Hello everyone. Today's webinar is on LED source integration in lamp design, with specific focus on designing PAR 38 lamps. I will be your presenter today. I'm Mike Govin, Vice President of Sales for Lambda Research Corporation. Today's format will be a 35 to 40-minute presentation, followed by a question and answer session. At any time, submit your questions using the question box in the GoToWebinar control panel. We have a lot of additional resources for this webinar. You can look at past webinars, TracePro tutorial videos, TracePro tutorials, and information on upcoming TracePro training classes using the URLs listed here. The current TracePro release is TracePro 7.5, which was released October 15th, 2014. This release can be downloaded by anyone with a current maintenance and support agreement at www.lambdares.com. Our agenda today is how to choose the right LED for the task, making an LED source property using the information and graphs from an LED datasheet or using array file source, setting up and defining a 3D reflector model for analysis and optimization, understanding the design problem and optimizing based on best optimization techniques, doing several reflector optimizations, adding curved facets and re-optimizing, adding a lens and re-optimizing, and finally creating IES files from the ray trace results. So what is a PAR 38? A PAR 38 lamp design consists of a parabolic aluminum reflector, PAR, source and lens sealed into a singular unit. But now that we've gotten into a modern day application, it's not necessarily that with the advent of the LED introduction into the PAR lamps. PARs come in different sizes. The larger the size, the higher the wattage the PAR lamp can output, and the larger the diameter of the lens sealing of the unit. In the U.S., PAR lamps have multiple sizes and applications and are measured in inches. PAR 16 and PAR 20 lamps are used in the retail market industry as accent lighting. Larger PAR 56 lamps are very big with higher wattages and are used in daylight situations where the lamps need to be very powerful, for instance, airport runway lighting. Finally, the PAR 38 lamp is medium in size, and the output is around 75 to 150 watts. And these are mainly used in theatrical applications for the film and stage industry. There are many types of PAR lamps based on their angular information. For instance, a wide flood is usually a WFL 70, medium flood 24, narrow spot 14, and a very narrow spot 12. In nations using inches, the glass envelope or lens of a lamp is measured an eighth of an inch. Thus, a PAR 64 is 64/8 of an inch in diameter, or 8 total inches. In the U.S., a PAR 38 lamp is approximately 4.75 inches in diameter, and in nations using millimeters, a PAR 50 lamp would be a 50 millimeter in diameter lamp. So, the first thing we need to do is to create a specification for a better PAR 38 lamp. So be careful in selecting your source. Do you have enough LED power to achieve your goal for the size of the PAR lamp you are designing? First, set an output specification. A reflector shape will determine if you can meet that objective. And for this webinar, we'll design using the specification below. The total lumen output for a PAR lamp, PAR 38, should be around 500 lumens. The angular output, the percentage of lumens into angular range, is going to be 14 degrees. It's a narrow spot for this task. The color, well, this is for stage lighting, so a CRI that's quite high would be much better for visualization purposes. So we're going to consider something between 80 to 90 CRI. Uniformity, we expect to have good uniformity. Since this is stage lighting, these lamps are going to be at least 10 to 15 feet above the stage. And finally, looking at the luminous efficacy, lumens per watt, we're expecting that's going to be over 80. And that's usually pretty typical for an LED lamp anyways. So let's look at some LEDs. In a past webinar, Dave Jacobson showed you the Seoul Semiconductor Accretion 2 13-watt, 1210 lumen flux lamp. You can see three data sheets here that show you the LED itself, its spectral distribution, and its angular distribution. So this would be one possibility. A second possibility, if you like bridge lux LED arrays, is the ES rectangular array on the left-hand side here, and the spec sheet for the higher flux output RS array on the right. Well, we're going to be probably getting about an efficiency of 50% for this lamp, so I'm going to need at least 1100 lumens for this particular application, and I want a 90 CRI. So the ES is about 19.5 millimeters in diameter. The RS array is about 31 millimeters. So for our particular size, and the size of this PAR 38 lamp, because it's going to be 4.75 inches on the output over here, we're probably going to go with a very narrow and a smaller ES array. And if I go and I look down the part numbers that I have available here, pretty much the BXRA 30G1200 meets my specification. 90 CRI, 1140 typical lumens when it's operating at about 85 degrees centigrade. And my total efficacy is about 89. So this is a pretty good setup, and this is probably one we're going to use. I'm going to show you a couple more options, but first, let's bring this particular array into TracePro. To do that, we use the surface source property generator. This allows us to specify the angular and spectral information and add this to our TracePro database. So first of all, most LEDs are Lambertian in their output, and we can see the beam shape profile editor over there in the top left-hand corner, and that allows us to put in the angular displacement. And then on the right, we've done a screen capture of the spectral information, and we're going to digitize this in and use that as our spectral information for this particular lamp. Well, what happens if we wanted to make an LED array of a whole bunch of smaller LEDs? Well, we could use a Cree XPE. This would be a great solution, but we need about 12 to 15 LEDs. This would add thermal aspects and more to this. But if I want to do that, I could digitize in this information and bring this in as my particular LED array in this case. So it looks like we need a pretty large LED to get the kind of output we're going to need for a PAR 38 lamp. So let's ask a few more questions here. Which LED solution should we pick? LED array, multiple LEDs, RGB LED, or a singular LED source? For ease of implementing this solution, a single BridgeLux 30G1200 LED array is the easiest and best optical solution to fit into our reflector, also best for a thermal heatsink. Next question, what shape should the basic reflector be? Cone, parabola, or freeform? Let's try all of them in this particular webinar. The next question, should we use glass and use total internal reflection, or reflector material for the optic? For this design, we're going to assume that the reflector surface is aluminized because we're doing a PAR lamp, and having PAR, reflector type, that's the one we're going to go with, although we could use a coated glass. A dichroic coating would pass IR heat out of the body, but this is more of a factor for non-LED lamps, so we're just going to go strictly with a reflector here. Now, is a diffuser needed to soften the look and hide the LED array itself if you look directly into it? That's a good question. We can look at that. Are curved facets needed? What type of facets are needed to meet specification to create a softer look? And specifically, can we use these facets to move light from the middle area out to the edges if we need it? Let's look at a couple of examples that are out there. The PAR 38mm Philips LED example. This is it. It has about 8 LEDs. It's 121.6 millimeters in diameter and about 129.3 millimeters in length. Once again, 4.75 inches in this lens opening in the front. It gives out 1,050 lumens, and the full information is here, but this particular Philips bulb is giving out 25 degree angular output. This is a little bit larger than the 14 degree full width half max that we want with our particular lamp, but it gives us a good idea of what we would need to create an LED type lamp. In this case, they don't really have a reflector. You've pretty much got the LED sitting there right at the top. Let's look at an old style halogen example of a PAR 38. Once again, it's 4.75 inches in diameter, about 5 inches in length, and this picture and specification is courtesy of PlusRite. So here's your average 45 watt, 525 lumen, medium flood that we're trying to duplicate, except that we want a smaller angular output. In this case, this one happens to be a 30 degree. We want a 14 degree. So pretty much what we're trying to replace here. Let's now set this up in TracePro. If I set up the reflector, the ES array, and a target surface 10 feet away, this is what it looks like in TracePro. We're looking from the back end towards the target surface. Looking into the reflector, this is pretty much what you have. We've got to set up the BridgeLux ES array, the reflector, and you see that the ES easily fits in the reflector shape that we start with here. The next thing, We want to make the base large enough to accommodate the LED, but we also want to make sure that the outer edge of the reflector gives us that 14-degree full-width half-max. So we're going to sketch this into the 3D Interactive Optimizer to create the shape that we want. We're going to check the starting design by tracing a few rays out of it, and you can see that with the yellow rays coming out of here that I've traced using the ray option in the surface dialog. And we can see that we have a very good mix here and a fairly good angular output close to what I'm looking for. So the interactive ray tracing capability allows me to start with a pretty good starting design, so I start with a good local solution. So if I put this into TracePro and I ray trace it, I'm going to try to show you that I see a 3D illuminance on the left-hand side of TracePro. I set up an angular distribution, a rectangular candela distribution, in the top right-hand corner. And down in the bottom right, I'm going to show you an illuminance plot so I can look at uniformity and what my max and minimum values are on the target. So for this particular analysis and this particular starting design, I have about 20% efficiency. So 20% of my light hits the target. All output is shown in linear space, and if we use the optimizer, we should be able to get something better. In my rectangular candela plot, we see that at -7 to +7, I have half of my energy. So I have my 14-degree full-width half-max. So now, I want to use the 3D Interactive Optimizer in TracePro to specify variables, add optimization operands, for instance, full-width, half-max, uniformity, and total flux to improve results. So we're going to use the analysis tools in TracePro to verify these results. So we're going to use the Interactive Optimizer to sketch in the reflector, sketch rays to start with a good initial design and check that, and then optimize using the user-defined mirror function we specify. We're going to check all the different reflector surface types and optimize them. For this demonstration, we'll optimize conical, parabolic, and freeform solutions for the reflector shapes. We're going to use the irradiance/illuminance maps to check efficiency and uniformity, and candela plots to check the full-width half-max to make sure we're hitting 14 degrees. And finally, we're going to use path sorting to see ray paths. So for this particular reflector, here's how I would set it up in the 3D Interactive Optimizer. In the surface area, I would create the reflector itself and the segment points. In the property editor, I would specify that these are variables, the edge around the base and the outer edge, and that they can move back and forth. I would then specify in the optimization dialog my operands, and in my object view I could see the 3D object, which is a 2D sketch spun around to create the conical reflector that I'm looking at. I would then specify a surface property of the perfect mirror in the property editor to finish up the interactive optimizer setup. Let's blow up the optimization dialog. You can see that I have three operands here. I have full-width half-max, total flux, and uniformity. This is going to allow me, if I want to use all three, to give me all the information and to create a mirror function that solves all this for me. But I can specify weights for each one of the target values, and we'll talk a little bit about more on the operands and everything else and which one I'm going to use here. But for this starting one, I'm going to say that the beam width, the full-width half-max, is the most important, which it is because I'm trying for a 14-degree full-width half-max lamp, but I also want to have uniformity. I want to get as much power as possible as well to my target. So this is crucial. But the most important one is full-width half-max of 14 degrees. So if I go and I start and I look for the linear conical reflection before optimization, I've got 18 degrees with the setup that I started with. I have my 14-degree full-width half-max, and you notice I have very good uniformity. But 18% of 50 efficiency, I'm really looking for 50. So I start setting up the optimization. I start it off. So the first iteration of the optimizer log, the first iteration of the optimizer log, appears after the completion of the first ray trace. The first operand error function, variable definitions, and time taken are shown for each iteration in the optimization log as a row in the spreadsheet. A lower error function indicates a better solution and is shown highlighted in red. We can see this on the right-hand side, where I have an optimization log with 7 iterations. Now this allows us to monitor the downhill simplex method that we're using in the optimizer. all of the graphical plots for each iteration can be seen in the plot. So for instance, if I'm looking at a couple of operands, each operand I can see the results for as it iterates. So for the first iteration, we're looking at a graph of the candela plot, which is the first one. And if I use the graph selector slider bar, I can slide it to the right and see the uniformity. So by looking at each iteration, I can then go back and forth and see what my output looks like. So for this case, sliding the selector arrow to the left shows the polar plot, and to the right the uniformity on the target surface. Well, there's another thing that pops up into the optimization log. I see that I can look at the graphs, but I can also look at the trend chart. The log shows the best iteration, highlighted in red, and plots the downhill simplex error function, showing the downhill optimization as a function of color in the trend chart. Generally, the error function should show downward as the iterations progress. So pretty much what's happening here is that as the downhill simplex operation goes along, it's going to be doing different functions to try to find a local solution. These are shown in the legend on the left underneath the trend chart. So for instance, there are 4 different types of operations: reflector, expansion, correction, and shrinkage. And so these are shown as you go through. Now since this is downhill simplex, we should see a downhill trending plot here. And this is error function versus iteration count. So if the downhill simplex method is working correctly, what we should see is the program going back and forth, up and down, trying to find a local minima, sometimes getting a much larger error function, sometimes getting a lower one, but definitely trending downward as we get 20 to 30 iterations into the operation of the optimization. So now, once we optimize, we can come back and take a look. We'll see what's happened here is that I have 19% efficiency with a maximum luminance of 561 lux in the center, but in terms of the optimization here, I didn't give it enough degrees of freedom. I got a very poor answer really in terms of what was happening here because I was just using a linear conical reflector. It looks like this is not going to make it in terms of my solution. So I'm going to have to look at something else here. Well, a PAR is a parabola supposedly. So let's look at a parabolic reflector now. So I'm going to do the same thing I did with a linear conical reflector. I'm going to set up a parabola. I'm going to specify some variables, which is what I'm doing in the 3D interactive optimizer here. And then I'm going to look at the starting solution. So here I go. I have efficiency of 18.4% with that parabola. And here's my max luminance of about 643. And I've got a very unusually shaped rectangular candela plot there. But this is a good start. Well, what I'm going to do is I'm going to go through a few iterations, and that's what I'm doing here. I'm watching the optimization log. I'm making sure that things are getting better as I go along. And so what's wonderful about TracePro's interactive optimizer is I can keep a pulse on just what's going on while the program is optimizing. I can see the reflector shape. In case it goes to a non-manufacturable type solution, I can stop it. I can reset my variables or my merit function, and I can restart it again. And then I can also change my operands. And almost anything that I've set up, if I don't like what's going on, I can immediately stop it, and I can start being more productive by creating a better solution. So this is what's going on here. I can see I've got 22. It's coming to a solution. Well, after the optimization, it looked pretty good. I did get good results. I got an efficiency of 25% with a maximum luminance of 1,064 lux in the center with 500 lux at the sides. So I've got a fairly good solution here, but it's still nowhere close to my 50% efficiency I want. So I'm going to add more variables. Whenever there's not a good enough answer, I add more variables and see if that's going to help. Well, in this case, I've added 3 segment points. I've allowed them all to be variables to move back and forth in that little box you see in the surface list there, the surface dialog. And I'm going to try re-optimizing again. Well, now, after the optimization, it's about 23%, but I do have better uniformity, but once again, I'm still not near 50%. So at this point in time, I'm going to flip back and I'm going to try a freeform reflector. I'm sorry, here I think I jumped up back here. This is a freeform. I come back, I look at the freeform start. The starting optimization is 23%. I then set my variables. Notice that as I got to optimization iteration 143, I started getting a good solution. When I do a rate path sort and I look at the light that gets to my target, the first third of the reflector has most of the power that reaches the target. Therefore, this first third segment is my most important. And as you see, I stopped the iteration on number 143, and that's exactly the shape that I'm seeing there. I've got a nice rounded shape around the base of the LED. So this meets my angular target, shows me maximum flux, and gave me better uniformity than the optimized cone or parabolic reflector. In fact, when I look at this, I've got 26% after the optimization. Once again, I still want better, so I'm going to go and I'm going to start with a different local solution. So I'm going to change the shape of the reflector, and I'm going to try again. So with the downhill simplex method, having different starting points gives you different solutions, and I'll talk about that shortly. So now, with a different starting point, I have 16% efficiency, and I have very poor output. But hopefully I'm closer to a better local minima. And sure enough, I'm going to change something here. I'm going to optimize, and I'm going to add a flux target. I want to see if I can get the maximum amount of flux here. So I'm going to add that as well as I go through on this portion of it. And sure enough, when I do the optimization here, I get excellent efficiency, 41%, maximum of 845 lux in the middle, 650 lux at the edges, with 475 lumens reaching the target. This is very close to my ideal solution. And you can see what's happened here. If I look at the rectangular candela plot, I can see that there's more power underneath my curve. So that means that I've actually pulled the light in, and I've gotten more power when I want, and my uniformity is better. This is excellent. Well, how did we do this? Or how does the program do this? Well, it uses the downhill simplex or Nelder-Mead method for optimization, and this was first proposed by John Nelder and Roger Mead in 1965. The downhill simplex method is a local optimization method, meaning that it will converge to the solution closest to the starting point. It's possible that a better solution is available, and changing the initial starting condition can also be used as a test to see if a better solution is available. This is a good choice when optimizing geometry, position, rotation, where it's desirable to jump around solution space to find and then refine the best choices for variable values. There's more information on the downhill simplex method, and it can be found using Wikipedia and searching for the Nelder-Mead or downhill simplex method. So let's look at what we're doing with the downhill simplex method. Here's the theory behind it. The solution space for optimization problem is shown here. And you can see we have three solutions. The best one, of course, is on the bottom right. That solution space says I have three local minima. The deeper the trough, the better the solution. The solution space starts off where we set our first starting system. So in other words, when I created the conical reflector, when I created the parabola, when I created the freeform, these are all three different possible starting solutions. And of course, the one that's closest to the global minima is the one we want to find. So trying several different designs is going to really be beneficial for hopefully finding the best solution for you. If you only try one, you may get one of these poorer starting solutions instead of the good one that's over there on the far right. So how does this work? The Nelder-Mead method uses the concept of a simplex, which is a special polytope of n+1 vertices and n dimensions. Examples of simplices include a line segment on a line, a triangle on a plane, and a tetrahedron in three-dimensional space. A polytope is a geometric object with flat sides, which exists in any general number of dimensions. A polygon is a polytope in 2 dimensions, a polyhedron in 3 dimensions, and so on in higher dimensions, such as a polychoron in 4 dimensions. So let's look at a simple example for 2 variables. For 2 variables, the simplex is a triangle. The algorithm compares the error function at each vertex of the triangle, rejects the vertex where the error function is highest, and replaces it with a new vertex. This forms a new triangle, and the process is repeated, and that's one iteration for each time we repeat the process. The process generates a sequence of triangles where the error function at the vertices gets smaller and smaller, and the size of the triangles is reduced, and the local minima is found, finally. The method uses reflection, expansion, contraction, and shrinkage operations to generate the new vertices. So that's what you see in the legend on the trend chart in the optimizer log. So here's what they all look like in terms of these four operations. With reflection, we actually create a mirror of these vertices. In the expansion, we pull the triangle farther apart. In contraction, we make it smaller, as well as with the shrinkage operation. So in the optimization log showing the downhill simplex operations, you can keep track of the iteration in the first column, the error function next to it, and all the variables and what they're set to, and of course the time for each iteration. In the trend chart at the bottom, it shows you each operation as a function of color, so you know when the reflection, expansion, contraction, and shrinkage are occurring. And the downhill simplex method should look like a downhill trend where you finally get to a point where you're just looking very, very small amounts of solution space until you get to the one that you finally want. So the best practice for using the optimization operands can be shown in this particular design. As we can see from this analysis, trying different starting points using multiple operands and different reflector shapes create better designs. The full width half max operand was added recently to give users the benefit of optimizing users' very, very important specification, especially for this PAR 38 lamp. When you set the reflector shape, you should consider how the outer aperture clips the angular output and uses as the limiting factor of the reflector. Specifying the outer aperture size can be done as a variable, but simple math will lead you to a good starting point. Start with one operand and add more as needed. Using too many operands can cause conflicts by creating solutions that may not be optimum as they work against each other during the optimization. Adding more operands as you go allows the user insight on what an operand does for the optimization. For this optimization, adding the flux operand took the efficiency of the reflector from 26 to 42%. But be careful. Adding the wrong operand can create a dual angular peak solution, which creates a better uniformity overall, but creates dark and light patterns in the output solution on the target, which are discernible by the eye. Now, when we start off, how big of a solution space should we look at? The characteristic length is an estimate of the size of the solution space for an optimization process. It is used when defining the initial simplex. Each vertex of the initial simplex is a variable set that is a function of the characteristic length and a random number. The default setting is half the range of the variables. It is used only in setting the starting simplex of the optimization. So you can see here that you can use two different characteristic lengths, determined by the ratio of limits or determined by length. The defaults are 0.5 for the ratio of limits and 0.1 by determined by length. The stopping condition I'm going to talk about on the next slide. And after you have done the optimization, you can have it revert back to the starting point, the end point, and the best point, depending on the settings you set in the configuration for the downhill simplex algorithm. So for instance, if we look at stopping conditions, these can be set in three different ways. Well, first of all, the goal is reached. Second of all, how many iterations do you want to take? I mean, if an iteration of 5,000 is good enough for you, that's the default. But usually I'm thinking possibly 100 to 150 is usually the default number you're going to be looking at here. And then finally, an iteration tolerance. If one iteration is no different than the next iteration by 0.0001, we stop the optimization. If we look at adding curved facets to the reflector design, we can see that this creates a softer look for the particular reflector. But in a lot of cases, it's not going to give us better efficiency. If we select the hexagonal type of reflector, curved reflector geometry, with 15 steps from the edge of the LED base all the way out to the output edge where the lens is, and we specify 15 rings, this is what it's going to look like. Now if we select the hexagonal type, we're going to get about an efficiency of about 30% here. So we get good output, but it's definitely not as good as the spline reflector. Adding more segments to the spline reflector creates more degrees of freedom during the optimization. And if we had done this with the freeform before, we probably would have got better efficiency, but I'm going to do it right here, right now, and I'm also going to keep the same operands to see if I get better answer. Well, what's going to happen here is I'm going to get segments on the area around the LED where I have the most critical amount of light coming out, and this is going to really broaden out my angular output and give me better uniformity. And we can see here that I'm getting about 39% efficiency, which is quite good. So adding more degrees of freedom and more variables around the reflector is always a good idea. If we change to spiral facets, it's not going to improve the design. And I did try several different spiral faceted designs, but it dropped to about 31% efficiency, and I didn't get the answers I really wanted here. Finally, let's add a lens to the mix so we get the sealed beam for the PAR. So what I'm going to do here is that we can look at adding a lens that's flat on the top, or I can have it flat on the bottom, or I can put the curvature on the bottom or curvature on the top. In this case, I put the curvature on the bottom, and I allowed the control point to move back and forth, which is shown by that orange box around the green dot in the surface list dialog. Then I kept everything else the same. I then re-optimized. So pretty much this is what it looks like. So I've made the reflector solid. I've made the lens clear so I can see into it. I can see the spiral facets on the outside. Adding a lens is going to create a loss of about 5% per surface because this is the Fresnel loss that all lenses have. So you're going to think twice if you're going to need one. But there's a really good idea for having a lens on a PAR lamp. It seals the beam, and it does not allow it to have corrosion over time from the elements, for instance, and from salt in the air. So therefore, if you live on a coastline or something of that nature, you're going to want a sealed beam here. It's going to create a softer appearance, but it's going to drop the efficiency. So you're going to have to make your reflector design a lot better if you're going to put a lens on this and try to hit 50%. Currently, we're at 26% for this particular lens optimization. We could also add periodic function to bring in more light. For instance, we could put little triangular or Fresnel facets onto the lens to do that sort of thing. We could also look at adding a texture so that we're hiding the LED array as well. For instance, a Moltec 11005 or 11007 type texture, which is in your catalog in TracePro 7.5, would allow you to do that. Now, there's something new in TracePro 7.5. This allows you to bring up any Candela plot, right-click to get the Candela options. You'll see a new option in the list that's open in IES/LDT analysis. You no longer have to save one and then bring it into the IES/LDT to further analyze it. By just clicking on the Open in IES/LDT analysis, the menu item, boom, up will come up the IES/LDT analysis utility, and you'll be able to create custom plots or use the built-in ones, which I'm now showing on this next screen here. You can see you can output the built-in lamp information, illuminance analysis, and Candela plots for this particular analysis. You can also create your own, and of course these are perfect for putting on websites and giving as part of your reports. So I'm going to let this open for questions and answers. Currently I'm not seeing any questions, but you're going to find that this recording, as a matter of fact, is going to be on the website, and a copy of the slides will be available in the www.lambdares.com/webinars area. Thank you very much for attending. And as always, I hope that you enjoyed the webinar, and please look forward to the next couple ones that will be coming out. Bye for now.